Hello everyone, myself Meenal Gupta from Department of Innovation Engineering, University of Salento, Italy. Let's see the last part, part 3, on presentation on my topic hydrogen's potential in a clean, secure and affordable energy for sustainable future. In the last part, in the second part of my presentation, we have seen a few of the hydrogen production methods. We have covered coal gasification method and the hydrogen production using fossil fuels. Now, let's see the hydrogen production using this using nuclear energy. So, in production of hydrogen using nuclear energy, high temperature nuclear reactors are required. And in this nuclear reactor, the energy is produced by via splitting this reactor's atoms, and this energy is transformed, is used to transform water into steam. So this thermal energy is used in production of hydrogen for different methods. If it is used in turbine to generate electricity, it is the produced hydrogen is called pink hydrogen. And if thermal energy is used in this steam methane reforming technique, then depending on if it is without CCSU technique, it is called red or gray hydrogen. With CCSU, it will be blue hydrogen. And if this thermal energy is used in thermochemical water splitting for generating hydrogen, then the produced hydrogen is termed as purple hydrogen. Now let's see the hydrogen production using biomass. So already we have seen that it can be categorized broadly in two ways, biological and thermochemical ways. So in this biochemical route, this organic material, it is used to produce the biogas. And if the used method is in form of application of microorganism, then this process is termed as anaerobic digestion. And if the organic material is used to convert into this biogas with use of different acids and alcohol and gases, then the production method is called fermentation. In this anaerobic digestion, this is a very mature technology to produce the hydrogen. And but in this process, very limited kind of precursors can only be processed, like sewage sludge, agricultural waste, food process related waste, this household waste, and some kind of this crops, energy crops. So these only can be processed using anaerobic digestion for converting it into biogas. However, in fermentation process, even non-edible this cellulose part of this some plant, they can also be processed for producing biogas. In this thermogasification process, thermochemical gasification process, it is very similar to the coal gasification process. And here all of this organic matter, it is converted, especially lignin part of the biomass, it is converted into carbon dioxide, methane, carbon monoxide with hydrogen. So lots of plants, they are deployed based on thermochemical gasification in the world, but still this is not fully developed technology because of many drawbacks. And one of the main drawback is that in this hydrogen production method, there is a formation of tar, and which act as a poison for the used catalyst. And this problem is going to taken care by different researchers, but still this is not fully resolved. So we can say that in all such processes where the hydrogen is produced with this biomass biomass or other processes. So it need to be extract hydrogen because of existing other product also. Let's see the other drawbacks of this biomass production technology of hydrogen. So this technique is also not very simple technique. It is complex, and that's why it increases its cost. This is producing low carbon hydrogen with lots of expenses with respect to the solar or wind-based electrolysis process. And this technique also, it is not large-scale technique for hydrogen production, because there is a limitation in the availability of cheap biomasses. And still, this biomass production, it can be embedded easily with CCSU technique, using which this emission of carbon dioxide can be reduced. And therefore lots of researches are going on in finding the processes by which the process can be make more economic, and this technology can be scaled up. Let's see the hydrogen production method, which is electrochemical. So hydrogen can be produced with water electrolysis also. In this water electrolysis, this water is split into hydrogen and oxygen with the electrolysis with the electrochemical process. And in this process, if we want to produce 1 kilogram of hydrogen, 9 kilogram of water is required, and 8 kilogram of oxygen is created as a byproduct. So in such kind of production, if this is done at a small scale, then produced oxygen can be used in healthcare sectors. And if this method is used at large scale, then definitely this produced oxygen, it can be used in industrial purpose also. So, but still, this technology, using this water electrolysis, only 0.1% of hydrogen is produced nowadays. But whatever hydrogen is produced with this method, it is pure hydrogen, and that's why it is used in this electronics and polysilicon technology. This hydrogen, which is produced with electrolysis method, a part of that, 2% of the global hydrogen, it is produced with this chlorine alkali electrolysis process also, which is used for the production of chlorine and this caustic soda. The electric efficiency of this electrolysis process is between 60 to almost 81%, depending on which technology we are using. This water electrolysis, however, it requires the fresh water, and fresh water it can be a issue for those countries or those regions where water is scarce. So in those regions, there is a need to exploit seawater for the water electrolysis. However, using this seawater, it is not very friendly, because it can corrode the reactor, and it can also produce the chlorine. And therefore, lots of researches are going on that how efficiently we can use the seawater in water electrolysis process. So this electrolyzer technology is existing in 3 types nowadays: alkaline electrolysis, proton exchange membrane electrolysis, and solid oxide electrolysis. So let's see one by one. This alkaline water electrolysis, it is mature and this commercially available technology, and it is mostly used in where hydrogen production is done in fertilizer and chlorine industries. And this in this this alkaline electrolyzer, this caustic water solution is used with KOH as this electrolyte. And also this sodium hydroxide and sodium chloride, they are used as catalyst. And this electrolyte is used in the liquid form, and the reason is that in the liquid form, these ions can be transported easily between the electrodes, and therefore there is very less chances for the consumption of these electrolyte ions in the chemical reaction. And the principle is that here water is converted into oxygen and hydrogen with the help of application of this current. So direct current is applied here for splitting the water molecule. So we can see the reaction occurs like this. At the cathode, the two of the water molecules, they dissociates, and the hydrogen is generated. And at the anode, this oxygen arises, and another water molecule generated. So we can say that at the same time, the hydrogen is consumed at the cathode and it is produced at the anode. And in this alkaline electrolyzer, the used electrodes are generally nickel, copper, this iron, and this used electrolyte is KOH. And diaphragm is also used to separate the two electrolyzers. This is made of this, mostly it is nickel oxide. But disadvantage of this technology is that its efficiency is also low, and it produces the hydrogen which is not very pure. Let's see this proton exchange membrane electrolysis process. So it was discovered when the work was going on in resolving the operational drawbacks of this alkaline electrolyzer. And in this process, this polymer membrane is used, which allows only to pass this proton, this hydrogen ion. So in this process, at the anode, this water is decomposed with electrochemical reaction, and oxygen is formed here. And at the cathode, this hydrogen ion, which is you can say pass from this membrane, it is collecting here. So the collected this hydrogen ion, it takes the electron and convert into hydrogen. So oxygen is taken out from the anode and hydrogen is taken out from the cathode. And in this way, we can say that water is converted into hydrogen gas. Let's see the advantages of polymer exchange membrane electrolysis. So in this, because pure water is used in this technology, that's why there is no need of this recovery of this KOH or this any catalyst. And also this technology is this more attractive because here the reactors can be made in a small quantity also. So that's why they are more attractive in the urban areas. And therefore this PEM technology, it is able to produce this highly compressed hydrogen for decentralized production and storage of this refilling stations. However, there are few disadvantages also of this PEM electrolyzer. The main thing is it is expensive technology because of used costly electrodes materials in form of platinum. And there is a costly, membranes are also used. and their lifetime is also shorter than this alkaline electrolyzer, and overall cost definitely is higher, and that's why it is difficult to deploy them with respect to alkaline electrolyzers. Let's see the third type of which is solid oxide electrolysis cell. So this is the least developed electrolysis technique, and in this the used electrolyte is the ceramic, which is a low cost material, and this solid oxide electrolysis, it works at a high temperature, and here generally this steam is used as a heat source for the electrolysis process. So let's see the advantages. So advantage is it have a high degree of electrical efficiency, and because this high temperature is used for the electrolysis, so that's why there is less chances of this losses of reaction at the electrodes. And also this SOEC technique is taking lots of attention because unlike this alkaline and PM electrolyzer, this can be used in the reverse mode as a fuel cell for converting hydrogen into electricity. So in SOEC, lots of researches are going on that how to change these heating sources to make it more effective in terms of economical point of view, and in terms of its use also. So if this hydrogen, sorry, if there is a production of synthesis hydrocarbon, then it produces a lots of waste heat, and if that heat is used as in form of the steam in SOEC, definitely it can help in reducing its cost. Similarly, this nuclear power plant and solar thermal energy, geothermal energy, these kind of heat sources can also be used in SOEC as this energy source. But these using such kind of energy sources, this is not commercialized yet. And if we are using renewable energies, then definitely this production of this green hydrogen will be more offered by the companies to the market, and it will be more attractive in the state of if it is produced with this fossil fuel. But in the SOEC, there is also one of the challenge that it works at very high operating temperature, and therefore the used materials can degrade. So it can decrease its lifetime. Okay, in this slide, there is a comparison of three different kind of electrolyzers in terms of their efficiency and lifetime and capital expenditure. So we can see that the long term this electrical efficiency of this solid oxide action cell is higher than alkaline or this PM electrolyzer. However, this lifetime of SOEC electrolyzer is less than other kind of electrolyzers, and we can see that this capital expenditure is also high for SOEC with respect to alkaline and this polymer exchange membrane electrolyzer. In this slide, I want to show the comparison of this emission of carbon dioxide, which is produced in different kind of hydrogen production methods. So we can see that when in any of the method, if without this CCUS technology, the carbon dioxide production is really very high, and if it is used, the carbon dioxide emission can be restricted. And also, if we are using this renewable or this nuclear generation based hydrogen production, then carbon dioxide emission can be restricted. And here there is a cost comparison for the hydrogen production using different methods and different kind of feedstock. So we can see that depending on the feedstock, the green hydrogen production can have different cost. But if it is produced with electrolysis process, it is more costlier than the other green hydrogen production methods. It can nowadays it is around $6 to $8 per kg. And if hydrogen is produced with fossil fuels, then definitely it will depend on that which country is having more fossil fuels. There, the production will be more cost effective. Otherwise, it can go up to $6 per kg also. Otherwise, yeah, the countries which are having the fossil fuel, the cost of hydrogen is really less. And if this hydrogen production is embedded with the CCSU technique, then it increases its cost up to, we can say, $8 per kg. So with this, I want to conclude my presentation with the words that lots of research is going on in developing the new technology for making those such kind of methods which can produce green hydrogen with less emission of greenhouse gases. And lots of this hydrogen production technologies, they are commercialized, but still there is a need to make the hydrogen production at large scale with also there is a need to cut down their cost. And this International Energy Agency, which has given the pathway for this net zero emission mission up to 2050. This must be fulfilled with the deployment of green hydrogen in most of the countries. So with this, I want to stop my presentation now. Thank you very much for giving me this platform, for giving me the chance to present my work in front of you. Thank you very much.